Rahim. In today's video lecture, uh, we complete solve the problem set 15.2, and this is related to the power series. So first we define what is power series and its components. So first of all, we start with the power series. What is power series? So power series is basically students well know about in the previous semester about the Taylor series, Maclaurin series. So power series is the generalized form of all these series. So power series is a series of the form a power series. First we write the definition of power series. So power series is a series of the form summation n from 0 to infinity an z minus z naught power n, and if we expand then we write a naught plus a1 z minus z naught plus a2 z minus z naught square and so on. This is our equation number 1. So this is the general definition of power series, and in here z is complex variable and a naught is the coefficient, may be complex variable or constant, and an may be real or complex. an is basically a naught, a1, a2 in an, and an is basically a coefficient, and this coefficient may be real or complex. So z is complex variable. In here in this series, z is a complex variable, and z naught is the center of the series, and an is a coefficients. An is coefficient and it may be real or complex. So this is the definition of power series. So in power series, some variable are involved. So in here in this power series, the z variable are involved, and z is the complex variable. So if z naught is equal to 0, and z naught is the center of the series, then 1 becomes summation n 0 to infinity an z power n, and we write this a naught plus a1 z plus a2 z square plus a3 z cube and so on. So this is the power series with center 0. So this is a basic definition of power series, and in exercise or problem set 15.2, we check the convergence of power series and radius of convergence of power series. So we have note, and that note is every power series converges to the center z naught, or at the center z naught. It's mean every power series converges. converges must converge at one point, and that point is the center. And if center is 0, then we say that a power series converges to at 0, and because center is z naught equal to 0. So our next is radius of convergence of power series. Radius of convergence of power series. So we just check the what is the radius. If in one dimensional, if we have real line and we have real power series, this is 0, this is minus infinity, positive infinity, then radius is look like interval. And if series in complex plane, in complex variable, then a radius of convergence should be a disk or circle or some point in a plane. So radius of convergence of power series is defined as z minus z naught less than r, and this r is a radius of a power series. Radius of convergence of if z minus z naught less than or mean, okay, let's suppose this is your z naught, and these points are points of z, and then this is the radius of convergence, and distance from z to z naught is r less than r. If a series satisfied this condition, then r is the radius and z naught is the center. So this is the radius of convergence of power series, and z naught again center of power series. So the next question is how to find the radius of convergence and center of power series. So we have theorem. First we check the theorem, and theorem is if limit n approach infinite, we use the ratio test here, and in the previous semester students studied about the Cauchy ratio test. So this is similar to Cauchy ratio test. So if limit n approach infinite, a n plus 1 over a n is equal to L is the limit, and this is equal to 0, then radius is infinity. What is the meaning of infinity? Infinity mean this series converge for all z. If we choose any z from the domain, then series converge. So if this limit equal to 0, then radius is infinite. Okay, and the second is if limit n approach infinite, an plus 1 over an is equal to L but is not equal to 0, then radius is equal to 1 over L. Just you take the reciprocal of limit, then we get the radius of the convergence of power series. And the third case is if limit n approach infinite, an plus 1 over an is equal to infinity or approaching to infinity, then radius is 0. And in this case we have the only one point, and this node from every power series converging to the center z naught. So in this case the series converging at the point only at the center. So in this case series converges only at the center z naught. So this is the complete detail about the power series. Now we solve the problem set 15.2, question 6 to 18. So let's start question number 6. Solve the problem set 15.2, question number 8, question number 6, and in this question or in 6 to 18 question we find the this is power series, and we find the radius of convergence and center of this power series. So center is so simple, and this is z plus 1, and comparing this with general terms. And what is a general term? General term is an z minus z naught power n. So comparing this z minus z naught this, then we get the z naught is equal to 1. Z naught is equal to minus 1. So z naught is equal to minus 1 is the z naught is equal to minus 1 is the center of a given power series. This is 1. So this is the center of 1. Now we find the radius of convergence. So a radius of convergence is 0, infinity, or only 1 point minus 1. By using the theorem we discussed in the previous start of the lecture. So now we use I use the Cauchy ratio test here, and some modification here. We use the Cauchy ratio test with some modification. So by ratio test or Cauchy ratio test, how to apply the Cauchy ratio test here? This is limit n approach infinite an plus 1 over an. So in here we include this whole term an and an plus 1, not this coefficient. I include the whole term is an or an plus 1. So this is the modification. So this is so simple, and an plus mean 4 n plus 1 z plus 1 power n plus 1. And what is an? And an is 4n z plus 1 power n. So we solve this limit, and this is a 4n plus 1 over 4n dot z plus 1 n plus 1 over z plus 1 power n, and this is the magnitude. So this is equal to limit n approach infinite, and 4 power and 4 power n are cancel out, only 4 are remaining, and in here a z plus 1 power n are cancel out, and only we have a z plus 1. So note n are here because our limit on n, so this is look like constant, so limit of this is a mod of 4 z plus 1. Now we want to calculate the radius of convergence. So we know that Cauchy ratio test converge if limit is less than 1. Limit is less than 1. So we use this concept and calculate the interval of convergence. So this become a mod of z plus 1 less than 1 over 4. So comparing this with the general definition of radius of convergence, and that is z minus z naught less than r, then we say that r is the radius of convergence. So in here z naught is minus 1 and r is 1 by 4. So radius of convergence is 1 by 4. Now we solve the next question, that is question number 7. Okay, in question number 7, again first we calculate the center, and center is so simple, and in here center is pi by 2. So this is z minus z naught, the center is pi by 2. Just comparing with the original term, with original power series. Now we find the radius of convergence, and we again use the Cauchy ratio test, and that is equal to, this is equal to limit n approach infinite an plus 1 over an, and this is equal to, we use the 2 equal to sign in one line. This is not good, but I think I just want to solve the question in one page. So this is limit n approach infinite, and what is an plus 1, and in here an plus 1 is minus 1 power n plus 1 over 2n plus 1 factorial and z minus pi by 2 to n plus 1. This is n plus 1, and what is a n? This is this, we consider this whole is a n. So we take the reciprocal of this because this is in denominator. So we also write this 2n factorial over minus 1 power n z minus pi by 2 power 2n and take the its absolute value. So this become so this is the best way to solve the this limit. Associate the same terms, I associate the same terms like first term is minus 1 n plus 1, so I associate this minus 1 power n dot. Now we associate 2n factorial, so this is 2n factorial, and in denominator this is 2n plus 2 factorial. So we associate these two terms, and the last term is z minus pi by 2 power 2n plus 2, and associate with this z minus pi by 2 power 2n. It's mean the same nature of terms together. I associate the same nature of terms, and this is good to solve the limit. So I check this. This is minus 1, only minus 1. Take the absolute value of minus 1, that become 1. So these terms are when vanish now, and now here 2n factorial, and open this factorial. This is 2n plus 2. This is 2n plus 1, and this is 2n factorial. Now come here, this is zn plus 2 power 2 are cancel out and only become z minus pi by 2 power 2. So check this 2n factorial cancel out this 2n factorial. Now put the limit here, and if we put the limit here, and this become z minus pi by 2 square over infinite. So this becomes 0, and its mean radius of convergence is infinity, because if we take the any value of z, this series converges to 0. So for all z, we choose any z, this series is convergent. So its limit is 0, and then its radius is infinite, as we discussed in the previous theorem. Now we solve the question number 8. Now again in this question we find the radius of convergence and center. So in here we compare this with z minus z naught, and the center is iota pi. This is so simple. We directly calculate the center. Now we find its radius of convergence. So again we use the Cauchy ratio test. So by Cauchy ratio test we calculate the limit and approach infinite, and again we take this whole as a n or a n plus 1. So a n plus 1 over a n. So a n plus 1 over n plus 1 factorial and z minus iota pi n plus 1, and multiplying what is a n. So this become n factorial over n power n z minus iota pi power n. We just calculate this limit. Again we use the because these terms are more complex, so for simplicity we associate the same nature of terms, then easily solve. So this become n plus 1 power n plus 1 over n power n dot n factorial over n plus 1 factorial dot z minus iota pi n plus 1 over z minus iota pi power n. Okay, so we solve this limit n approach infinite, and we take the we write this n plus 1 power n, and n plus 1 and n power n, and we write this term, open the factorial in denominator, n plus 1, and this is n factorial, and in here cancel out the nth term, and this only becomes z minus iota pi. So n factorial cancel out with n factorial, n plus 1 cancel out with n plus 1, and in here we take just common n power n. So this become 1 plus 1 over n whole power n divided by n power n, and this is z minus iota pi. Okay, so these two terms are cancel out. These two terms are cancel out, and limit of this is e exponential, because we know that limit n approach infinite, 1 plus 1 over n power n is equal to e. So and we know that Cauchy ratio test converge if its limit is less than 1. So this is simple, and we put here e, and this become mod of z minus iota pi less than 1 over e. So this is its radius. So 1 over e is a radius, and iota pi is the center of our power series. Now we solve the question number 9. So in question number 9, again we find the radius of convergence and center of radius. So similarly in here z minus iota, so center is iota. If z plus iota, then center is minus iota. Now we again use the by Cauchy ratio test. We want to find the radius of convergence for radius of convergence of given power series. So again we check the limit n approach infinite, an plus 1 over an, and this is equal to limit n approach infinite. What is an plus 1? So an plus 1 is n plus 1, and this is n plus 1 minus 1, this is n, and 3 power n plus 1 dot z minus iota 2n plus 2. So what we an is a denominator, and take the reciprocal of this, and this become an is a 3n over n minus 1 z minus iota 2 power n. Now we solve this limit. So this is so simple. Again we associate the same terms, and this is this n cancel out this n, and n plus 1 over n minus 1 dot 3n over 3n plus 1 dot z minus iota 2n plus 2 over z minus iota power 2n. So simplify this. Again we also, this is infinite by infinite form, and we also separate apply this limit on this term separately, this term separately, and this term separately. No issue. So again we solve here by using the L'Hopital rule, or by using the taking n common, and if we use the L'Hopital rule, then limit of this become 1. So we write here 1, and this is 1 by 3, and this become z minus iota square, because 2 and 2 and cancel out each other, and limit of this is z minus iota square over 3. And we know that Cauchy ratio test converge if limit is less than 1. So we take here limit less than 1, and this become z minus iota square less than 3. And we will take the root on both sides to remove this square, and this become z minus iota less than root 3. So its center is again iota, and its radius is root 3. Now we solve the question number 10. Bismillahirrahmanirrahim. In question number 10, again we find the center and radius of convergence. So similarly, as previous questions, center is 2 iota. Now we find the radius of convergence. So by using the Cauchy ratio test, limit n approach infinite a n plus 1 over a n, and this is equal to limit n approach infinite, and a n plus 1 is z minus 2 iota n plus 1 over n plus 1 power n plus 1 multiply, and what is a n? So we take the reciprocal of this term, and this is n power n over z minus 2 iota power n. So we simplify these term, so this becomes z minus 2 iota n plus 1 over z minus 2 iota n, and n power n over n plus 1 power n dot n plus 1. So we solve this, so cancel out this and become z minus 2 iota, and in here we take the n power n common from denominator, and this become 1 over n power n dot n plus 1, and these two terms are cancelled out, and this becomes z minus 2 iota, and put the limit here. So this is e dot infinity. So this is the limit of this is this term is e, and infinity plus 1 is infinity, so this whole becomes 0. So limit is 0, so radius of convergence is infinity. The meaning of this is this is converged for any value of z. So we put any value of z, this series is convergent. So this is the radius of convergence of given series is infinity. Now we solve question number 11. Now we solve the question number 11. So again the center is 0, because we compare this z minus 0 power n. So z naught is 0. The main task is find the radius of convergence. Again we solve by the Cauchy ratio test, and this is a n plus 1 over a n, and this is equal to limit n approach infinite. And what is a n plus 1? A n plus 1 is a 2 minus iota, yes, 2 minus iota over 1 plus 5 iota. This is similar, and this is a z power n plus 1, and multiply 1 plus 5 iota over 2 minus iota z power n. Some type of mistake here. This is a power n. So this is power n, and this is whole power n, and this is power n. So this become limit n approach infinite, and this become this is power n plus 1. So we solve this 2 minus iota n plus 1 over 2 minus iota power n dot zn plus 1 over zn dot 1 plus 5 iota n over 1 plus 5 iota power n plus 1. So simplify this. So this is limit n approach infinite, and 2 minus iota, this z and zn cancel out, only z here, and this is 1 over 1 plus 5 iota. So we write this limit n approach infinite 2 minus iota over 1 plus 5 iota dot z. Okay, so the limit of this term is mod 2 minus iota over 1 plus 5 iota z, and this is converge if by using the Cauchy ratio test this is less than 1. So this become mod of z minus 0 less than mod of 1 plus 5 iota over mod of 2 minus iota. So this is z minus 0, 0 is the center, and take the mod. So if we take the mod, then this become under root 26, because square of 1 is 1, square of 5 is 25, so 25 plus 1 is 6, and in here 4 plus 1, so root 5. So z minus 0 less than root 26 over 5, so center is 0 and radius is root 26 over 5. Now we solve the question number 12. Now in question number 12 again, the same process adopt here, and I am really boring because all questions are similar. So again we find the center, and center is 0 here because we compare this term with z minus z naught, and in here z minus 0, so z naught is 0. The main target is radius of convergence, and so we find the radius of convergence, and we directly put the value, apply the Cauchy ratio test here. So this become minus 1 power n plus 1 z n plus 1 over 8n plus 1 multiply 8n over minus 1 n dot z power n. So this is limit n approach infinite and minus 1 power n plus 1 over minus 1 power n plus 1 over n z n plus 1 over z n and 8n over 8n plus 1. So solving this become 1 because we take the absolute value, and in here we using the L'Hopital rule, and this become 1, and in here z and z cancel, only z, and in here 1 over 8. So this becomes z dot 1 over 8. So Cauchy series ratio test converge if a limit is less than 1, so mod of z less than 8. So in here z minus 0 less than 8, so center is 0 and radius is 8. Now we solve the question number 13. Okay, in question number 13 again we find the center and comparing z plus iota with z minus z naught. So z naught is minus iota, so center is minus iota. Now we find the radius of convergence, so using the Cauchy ratio test, and this is again apply an plus 1 over an. So this is limit n approach infinite. What is an plus 1? 16 n plus 1 z plus iota 4 n plus 1 over what is an 16 n z plus iota power 4 n, and we simplify this, we become this is 16, and in here z plus iota power 4, because 4 and 1 cancel out. So this limit is 16 z plus iota power 4, and we know that ratio test converge if its limit is less than 1, so we become z plus iota power 14 mod less than 1 over 16, and z plus iota mod is less than, we take the 1 over 4 power on both sides, and this become 1 over 16 power 1 over 4. So we write here z plus iota less than, and this is right 1 over 2 power 4 power 1 over 4, 4 cancel out, so this becomes z plus iota less than 1 by 2. So center is here minus iota and radius is 1 by 2. Now we solve the question number 14. I think question number 14, 15, 16, 17, do yourself, and in comment section write its center and radius of each power series. So I am waiting for your reply. So question number 18, solve again by using the ratio test, and I think first we find the a center here. So z minus z naught, and this is 0, so center is 0. So applying the Cauchy ratio test, and that is limit n approach infinite an plus 1 over an, and this become limit n approach infinite. What is an plus 1? An plus 1 is 2 minus 1 power n plus 1 over root pi 2 n plus 1, 2n plus 3 and n plus 1 factorial z power n plus 1. So this become 2n plus 3. Multiply an. What is an? Root pi 2n plus 1 n factorial over 2 minus 1 power n z power 2n plus 1. Now we calculate this limit. In here 2 and 2 are cancel each other, and we take the absolute value, so negative become positive, and this root pi also cancel each other. So we have only terms, that is z 2n power plus 3 over z 2n plus 1 dot multiply 2n plus 1 over 2n plus 3 and multiply n factorial over n plus 1 factorial. Now solve these terms, so this become limit n approach infinite, and this is 2n plus 1, and this is z square after simplification, and in here we use the L'Hopital rule, and after applying the L'Hopital rule, this become 1. Yes, this become 1, and open the factorial in denominator, so this become so in here if we put the infinity here, z square over infinity, and this becomes 0. So radius of convergence is infinity, because we put the any value of z, our power series is convergent. So in here radius is infinite, and center is 0 from here. So this is the problem set 15.2, and hopefully you understand the concept of power series, and if and you are able to check the radius of convergence and center of the power series. Thank you very much. Keep watching. Jazakallah.